So let's move on to the second presentation. The title of this presentation is Airport Passenger Flow Prediction using Simulation Data Farming and Machine Learning. And the authors are Roberto, Salvador, Félix, Patrón, Paolo Scala, Miguel Mujica Mota, Alejandro Murrieta Mendoza. So we have the video ready, and if we just share it.
Hello everyone, my name is Roberto Félix, and today I will present to you the results of our research project called Airport Passenger Flow Prediction using Simulation Data Farming and Machine Learning. The co-authors of this paper are Paolo Scala, Miguel Mujica Mota, and Alejandro Murrieta Mendoza. The contents of this presentation, I will start by defining the research problem, followed by the literature review, the methodology, for which I will explain first the real data, the data farming part, and the trajectory prediction, followed by the results, and finally the conclusions and future work. The research problem, this is a study case for a large-scale European airport, and this project is part of CESAR under the name Integrated Multimodal Airport Operations for Efficient Passenger Flow Management, or IMHOTEP. The objective of this research problem is to improve the efficiency of the use of resources and space at the airport terminal using machine learning and data farming techniques. Literature review. Mostly other research focuses on security control and check-ins, for which they analyze the passenger flow by analyzing walking speeds or passenger preferences, shopping preference or dining preference inside the terminal, but mostly focus on bottleneck elimination. The problem that we have is that the data that we have is time series, so we want to know where the passengers are at all times. So for example, we need to know the position of the passenger, but also the direction of the passenger, for which it complicates a little bit the implementation of machine learning algorithms. This data may be random, the data is non-linear, unstable, and usually there's not enough data. Our focus on this project is to predict trajectories based on data that we will generate from our simulation. Simple machine learning techniques are usually not able to deal with the data that I just discussed, so the nonlinearity and randomness, which means that more advanced machine learning algorithm techniques should be implemented, such as neural networks. But for this, the problem is that large amounts of data are required. So we thought that data farming may be a solution for that. For us, data farming is the process to generate synthetic passenger data through an airport simulator, in order to generate the passenger trajectories. For us, the most appropriate choice is to apply recurrent neural networks, because we want to know where the passenger is going, but we need to understand the whole trajectory of the passenger and not just the previous point. So we would like to know where are they going to, and based on that, do an analysis of the whole trajectory. The problem with recurrent neural networks are that these are difficult to train and suffer from short-term memory. The term LSTM, or long short-term memory, it's a specific cell that is added to the recurrent neural networks, which increases the short-term memory. So it will allow us to go a little bit further back within the context of the passenger trajectory. As you can see, the structure of the recurrent neural network and the recurrent neural network with the LSTM cell is exactly the same, plus the memory cell that's added to the recurrent neural network. For the methodology, here you can find the global algorithm. First of all, the real airport data that we have will be used for two different things. So one of it will be given the date, the airline, the city, and the type. This data will be fed to the airport simulation in order to create the data farming process, for which we will create the passenger trajectories. At the same time, the real number of passengers and gates will be used in order to generate these trajectories at the end of the algorithm. However, we thought that it could be possible that at some point the airport doesn't have the real information on the number of passengers and gates. So we will use also the real airport data in order to create a prediction of a number of passengers and the departure or arrival gates for a specific flight. As for the real data, we'll use first real data from the 1st of July of 2019 to the 30th of August of 2019. A total of 20,648 departure flights will be analyzed. We will not analyze the arrivals because we consider that passengers usually spend less time in the shopping areas of the terminal when they're arriving from a flight. We will consider commercial flights for the European Schengen space, European non-Schengen, and national flights over 50 passengers. We picked this number arbitrarily. And the first objective will be to predict the gates and number of passengers departing for each flight. Coming back to the previous diagram, we use the real airport data in order to make a prediction on the number of passengers. As we can see, we have a predicted number of passengers and a real number of passengers, which we will compare later in the passenger trajectory prediction. But the real data will also be used to feed the data farming process, which is to create passenger trajectories from an airport simulator. The real scheduled data is fed to the airport simulator. With this data, so knowing the amount of passengers, we created a total of 24 passenger profiles arbitrarily by the authors in order to create trajectory diversity inside of the airport. So we wanted to have 24 profiles in order to a passenger arriving at the gate may go through the shopping, may not go through the shopping. And that way we can generate the type of trajectories that a passenger will usually take inside the airport terminal. We simulated a total of 6 days of flights, and our airport simulation has a total of 135 airport objects, 79 gates, and a total of 46,020 passengers were implemented. Here's another picture of our airport model where you can see that the gates, the shopping area, and the catering areas are defined in a very high level of detail. Here is an example of one passenger trajectory. So I will explain the numbers on the left. The numbers on the left is the number of the object. So for example, object number 70 represents the Terminal 2 check-in, and we have a timestamp for one of the passengers. So you can see that we can track all of the objects that were visited by the passenger as well as the time where the passengers were there. Here's an example of the information that we have. So we have a flight on July 7, 2019 at 6 p.m. from this airline, this city. We can see that the real amount of passengers was 153 and the predicted number of passengers is 142. So it's not an exact number, but it gives us an idea of how many passengers will be per flight. And the gates, the real gate was 63. The predicted gate was C40, which is not exactly the same gate, but it's the same terminal, so the same shopping areas and catering areas that the passengers will visit. Here's an image of the check-in area of this airport. We can see that for the check-in area, which was the most visited object, we coded it as red, so anything over 3,000 passengers, which means that this will be a conflict area at this particular time. If you can see in the security area, it's yellow, so there are not going to be as many passengers at that time, of course, because there's a bottleneck in the check-in area. Here are the differences. In the previous one, both real and predicted data were in red. Here, however, if we compare the real data and the predicted data, the small difference that you may see is that, of course, in the real data and the predicted data, they may go to different departure gates. But what's important to know is that the passengers will be visiting the shopping and dining area in this part of the airport. And of course, the access to Module C or Terminal C will be congested. As for conclusions and future work, the passenger and gate data difference between the real and the predicted data doesn't have a big impact on the visualization for congestions. So of course, we would like to use real data if available, but if the data is not available, of course, we could still use the predicted data from our algorithm. the tool that we created could help predict visit points at the airport terminal at a given time and therefore help the airport operators. And as future work, we would like to improve the details on the passenger profiles because we believe if we can improve the detail of these profiles, we can generate more diverse trajectories. And of course, with this information, we could give the airport an overview of the type of shops, dining options, gate lounges, etc., that will be better suited for this specific type of profiles. And that way the airport can benefit from it. Thank you. These are our contact emails in case you want to discuss anything about the project.
Thank you very much, Roberto. Roberto, are you there? If you turn on your camera and microphone, maybe we can start a Q&A session. Thanks a lot for your recorded video, for your presentation. Very interesting work. I was part of it, so I know the efforts that was made in this work. So we have 5 minutes for questions and answers. So if anyone from the audience wants to ask a question. So we have one hand raised by Mohayed El-Bashir. Please, you can unmute yourself and ask your question.
Well, good morning. Thank you very much for the very interesting presentation and very interesting research work. Basically, I have some questions about from one side, the nature of the data that you used and the real data. It was, as far as I remember, it was from 2019. So this is before the COVID pandemic. So could you say something about this, the COVID pandemic, maybe the future research work that you're trying to do, for example, to address this particular issue? And from another side, something that I haven't understood so well, maybe you can elaborate more about the 24 profiles of the passengers. If you could say something about that. Thank you.
Well, hello. Hello, everyone. Thank you for your question. And well, I would like to apologize in advance because we had to feed like an usual 20-minute presentation in a 10-minute video. So of course, there were things where we went a little bit quick. To answer your question, so yeah, we took scheduled data from 2019, and that was the real data that we have from a specific airport. And we use that data for two things. So first, we use it to have a schedule as an input for the simulator. So in order to create the amount of passengers that will be at the airport terminal during the period of 6 days. And we use also the data from 2019 to predict the amount of passengers that would be at the airport at any time, in case we didn't have the real data in order to create the trajectories. So we used 2019 because that was the data that we have, and I think for this specific type of research, the pandemic would not have an influence in the data that we have, because what we use the data, well, it will have an influence for the prediction of amount of passengers, right? That's something that will change, but I think it's very complicated to make predictions based on the pandemic on how many passengers will be at the terminal, because 1 month you can have a lot of passengers and then they restrict travelers and then you have less passengers. So I think for the future it will be better if we try to stick to the flights before the pandemic and then see how it goes once all the regulations are over for the next couple of years. I think that was your first question. Your second question was related to the 24 passenger profiles. So Paolo here came up with the task to create 24 different passenger profiles. We created the profiles arbitrarily, so we defined a specific age, weight of the people, like walking distance, shopping preferences, and many things like that. So we did 24 of them in order to have diversity when creating trajectories. So we don't want all the passengers going from the check-in to the departure gate at the same time. We want some of them to go in maybe to to shopping, some of them to dining, some of them maybe wandering around the terminal. So that's what we wanted to do with the profiles. And of course, for the future work, ideally we'll have specific passenger profiles that we can have maybe from a survey at an airport, where we can give precise specifications for each one of the profiles, so we can make our algorithm more accurate.
Thank you, Roberto, for your answers. Yeah, actually, if I can add on it, because I contributed on this work and I was working on the simulation side and the data farming, while Roberto was working on the machine learning algorithm. And one of the main challenge here for me as well was the availability of data, because if we had data about passenger behavior or characteristics, we could have really used that for creating more reliable and real profiles. While here we have created those profiles which are, yeah, as Roberto said, arbitrary created by us. So, well, but that gives us room for yeah, future development. And yeah, we are already working on a follow-up to make it more accurate. Okay, if there are no any more questions for Roberto, I think we are in the time frame, so we can move on to the second presentation for this session. The title of
Yes. So thank you everyone for attending to my presentation. Thank you for your questions.
Thank you, Roberto. Thank you, Roberto. Second presentation, OptSim approach for the gate allocation problem in COVID-19 times. The authors are myself and my two colleagues, Margarita Bagamanova and Miguel Mujica Mota. So if we can start with the video presentation, please. Hello, everybody. This is Paolo Scala from the Amsterdam University of Applied Sciences. And the title of my presentation is OptSim Approach for the Gate Allocation Problem in COVID-19 Times. It's been already 1 year and a half that we are living with this pandemic, COVID-19, and it has changed many of our activities. If we consider airports, also many of the airports' operations and process have been affected by the new regulations due to the COVID-19. For example, the wearing of a face mask and especially the social distancing has really affected the operation. So has brought new challenges to the airport operators. And especially because airports can get really crowded with people, and of course having crowded places is not good for the transmission of the pandemic. So in this study, we want to investigate basically the gate allocation problem, which is basically assigning a flight to available gate at a specific time, considering operational constraints. And among those operational constraints, we want to include the COVID-19 regulations. Consider that if you would assign a gate in a terminal, as you are seeing now in this figure, you might really impact the occupancy level and the density of the terminal. You see here all these red lines and dots, they represent the density of people. So if we make a smart allocation problem, we might have a more spread allocation of gates, and therefore also more spread density of people within the terminals. So basically, in this work, we want to solve the gate allocation problem by considering COVID-19 restrictions, and we want to avoid to create areas with high density of passengers. We will do that by implementing an optimization simulation methodology, and we will use an optimization algorithm coming from the evolutionary algorithm to come up with the optimal or suboptimal solution. And we will use simulation techniques for evaluate this solution. The gate allocation problem, as defined in the work of DAS, is defined as allocating a flight to a specific gate at a specific time, considering constraints such as aircraft size, passenger working distance, and many others. As you can see described in this picture, basically we have a set of flights. For each flight, we need to assign a specific gate with a specific time. We also need to consider constraints such as the aircraft type, because not all the gates can accommodate different aircraft, because some aircraft are bigger than the others. So in this methodology that we have created, which comes from one of the referenced work by the authors, we basically start with optimizing the problem. We find an optimal or suboptimal solution. We test it in a simulation environment, and we test its feasibility. And so the gate allocation problem in this context, we have basically included COVID-19 restrictions. How? So we have introduced a gate taboo list. Basically, a gate taboo list is the list of gates that cannot be where a flight cannot be assigned to them at the same time, because they are too close to each other. For example, in this case, we have in the first row bit 30, gate bit 30 cannot be assigned together with bit 31, 36, or 37 at the same time. In this problem, the objective function is of minimization, where we want to minimize the number of unassigned flights and the number of flight assigned to a taboo gate. So we want to avoid to assign flight to taboo gates. In order to do that, we have developed a simulation model of an airport terminal. As you can see here from this video, you can see the different areas of the terminal and the movement of the passengers. Because of those processes are really variable, we have modeled them with stochastic variables as well, as you can see in the table at your left. We have chosen, we have used a case study, but we want to keep it anonymous. So we're not going to share the details of the case study, but we will share with you the preliminary results. So if you look at the table on top, we see the results from the original gate assignment, and we have 64% of flights either unassigned or assigned to taboo gates. The evolutionary algorithm optimized this solution, improved this solution. Indeed, we reached 23% of flights assigned to taboo gates or not assigned flights. So with the optimization, we improved the solution. But then let's see how the simulation results are. We will divide the results according to the different modules of the terminal, because this terminal is a big one and it is divided in different areas, namely module B, C, and D. So we will focus on each of them. Regarding module B, as you can see from the slide, on the left, you have the gate area occupancy, so with passengers, of the original solution, and to the right, the optimized solution. We can see already that the original solution has different, let's say, conflicts. You can see with the black crosses. We already detected 5, while for the optimization, we only have detected 3 conflicts. And so we have improved already. And we go from a maximum of 570 passengers, which are in this area among the taboo gates to maximum 370 passengers overlapping among the taboo gates. So we don't have an optimal solution, but we have improved at least. Module C, we have basically in the original solution one conflict with maximum 60 people overlapping, and in the optimized solution basically we have no overlaps. And as well as for the module D, we have only 2 occasions where we have basically conflict with the passenger staying in the gate taboo. And with the optimized solution, we are able to basically improve and having no conflicts at all. So finally, to conclude, the main findings told us that the methodology is able to decrease the passenger occupation in the taboo gate, so effectively improved the solution, original solution. But we also realized that we weren't able to find an optimal solution because of some areas were more difficult to be solved as other areas. For example, module B was more difficult than module C and D. So the layout of the airport is something that should take into account. And for further development, we can basically improve our methodology by considering also the number of passengers expected in the objective function. Also, we could get more detailed results from the simulation, and also on the operational point of view, we can also apply different policies and try to improve the solution. Thank you very much for your attention. That was all, and if you have any questions, please ask. Thank you. All right, this was my presentation. So now we enter in the question and answer session. So please, if you have anything you want to ask, any remark you want to make, you can raise your hand, or yeah, we have already Mohayad Al-Bashir. Please, you can unmute yourself, you can ask a question.
Thank you again for the very interesting presentation. Basically, I noticed that maybe you can link the 2 works, the first and the second, and applying it for the COVID context also. And this would be something really interesting to see for future research. And basically, I have just a question on the optimization technique that you've used. You noted that you used something, the evolutionary algorithm. I'm just wondering, how did you implement this, technically? Did you use, for example, a feature on the simulation engine that uses this, or you outsourced it from another optimizational tool, let me say? So if you could say something about this, thank you.
Oh, thank you for your questions. So to answer the first question, well, we this work and the previous one, we used the same case study, and of course different point of views. One is gate different problems. One is the gate allocation problem, and yeah, another one is more about predicting flow of passengers, which yeah, as you said, they could be integrated. Maybe, yeah, probably we could integrate maybe the prediction of the flow in considering the COVID restrictions, and yeah, that would be. I'm just thinking now, that would be a nice follow-up. Regarding the second question, okay, we developed the gate allocation problem algorithm, which was not in the simulation engine, so it was outside the simulation environment. So it was something apart, and my colleague, one of the authors, Margarita Bagamanova, actually, I think I see her in the audience. She is the one who developed this algorithm some time before, because she was working on this problem. So actually, this work was a cooperation between her research and my research, and we said, okay, let's combine your algorithm, and we put more restrictions related to COVID in your algorithm, and then we run it, and then we run it also with via the simulation. So those two elements are separate, and yeah, for the moment they are separate. So if I
could you say something about the integration of the two works? How did it was technically done? I'm asking basically about two things. The first, the simulation engine that you've used, and maybe the source code of the optimization algorithm.
Yeah. Well, the simulation environment, basically, I've developed a simulation model of this airport terminal by using a commercial simulation software. It's called CAST, and it's a really specific purpose simulation software. It was developed by a German producer. And yeah, it's specific because it's really specific to airports. So it's basically an agent-based simulation engine. So I could, they have a library of objects all related to airports, and that's how I could develop the model. Regarding the optimization algorithm developed, it was developed, if I'm correct, by using or C++ code, or I'm not sure. Maybe Margarita can tell me more. Margarita, are you in the audience?
Yes, I'm here.
Which was the code, the programming language?
So the evolutionary optimization algorithm was developed in C#.
C#.
Yeah. Originally. So this is, let's say, the console application that was a standalone application, not integrated into the simulation model, but it was using basically the same flight schedule as input as the simulation model. And based on this flight schedule, the certain set of gates could be assigned and matched with the flights from this schedule.
Yeah. And basically what we did as a contribution, so Margarita was basically mostly working on the algorithm. She added an extra constraint, which in this case is the gate taboo list. So basically we couldn't assign some flight to the taboo gates, basically, or at least we could assign, but it would be a cost in our objective function that we wanted to minimize, basically.
Thank you very much. It was
thanks.
satisfying.
Thank you for your questions. All right, let's move on. Any other questions from the audience? I don't hear anything, so I think we can move on. So let's move on with this session to the third presentation of the day, which title is Investigation of Platforms at Railway Station Switch Area with regard to capacity using computer simulation. The authors of this work are Michael Bažant and Josef Bulicek. I think we have Michael here in the virtual room, and please, if we can play the recorded presentation so we can see the presentation.
Sure. Yeah. Just at the beginning, I need to ask Michael if if he's here and he would like to share it, or I have to do it in his behalf.
Yeah, hello, I'm here. I'm ready for the presentation. And if you have the video of my presentation, you can start it, of course.
Sure, thank you very much.
On investigation of platforms at railway station switch area with regards to capacity using computer simulation. My name is Bažant, and we prepared the paper with my colleague Josef Budíček. We both are from University of Pardubice. Some railway stations are located almost out of municipalities. For example, in the Czech Republic we can talk about railway station Prapor Baba, Krasikov, or some others. And in these cases, the walking distances are often too great from the railway station to the city center. Presented research is focused on one of possible options how to make railway transport more attractive for passengers. This option is based on moving the platforms to location out of a regional railway station if this place is located closer to municipality. Such a situation can be seen in the picture, where there are original platforms and also new platforms labeled as B-stop. A question that the railway managers must address is potential reduction in railway capacity and impact on stability of railway operation. Trains at platforms located out of station occupy station switch area, as well as the line section during boarding and alighting of passengers. Operational features such as delay and delay propagation, or we can talk about timetable stability, are the main indicators for this process. These features are assessed with microscopic simulation model that we created within simulation tool OpenTrack. Microscopic simulation model was applied as a base for the research. Model consists of general railway line with a length of 30 kilometers, and we consider 3 stations on the line: Station A, Station B, and Station C. Potential movement of platforms is tested in the case of the middle station B, and the platforms are moved approximately 750 meters to the line segment between B and C, as we can see in the picture. Railway line is double-tracked in the segment between A and B. The segment between B and C is modeled in both variants as single-tracked or double-tracked within the study according to selected scenario. Line is equipped with automatic block system, which is common nowadays for this kind of lines. There are 3 basic variants of timetable that were investigated. The scenario 1 has an individual timetable reflecting single-tracked operation between stations B and C. This timetable has 2 minor modifications differing in the position of platforms at station B. Scenarios 2, 3 and 4 are based on second variant of timetable designed for double-tracked operation in the whole line between A and C. Again, we can see these changes in the picture. There is a specific timetable designed for scenario 5 using infrastructure of scenario 3. We will talk about it a little bit later. Now I will present results for investigated scenarios. The greatest difference in results was observed for scenario 1. The operation is consisted of 30 trains, of which 12 trains are stopping at B, and 18 of them are transit trains in station B. It was confirmed that changing the position of the platforms leads to a more significant impact on the value of the delay increment. In total, this is a change of almost 3 minutes, which is significant. In scenario 2, the situation is different because we count with double-tracked line between stations B and C. As we can see, it has positive effect on results in terms of average delay increment because it is negative value in both cases. In these two considered variants, it doesn't play almost any difference whether the platforms are located within railway station or outside. The same situation is in scenario 2, scenario 3, 4 and 5. As we can see, it doesn't make almost any difference whether we consider switch area between railway station and platforms or behind the platforms from the station point of view. The difference in scenario 5 is caused by extension of sojourn times of selected trains, so there is an option to cut delays in case they occur. At the conclusion, I would like to summarize the results. In case of scenarios with single-tracked line, there are significant differences in delays, and the delays increase when platforms are moved out of the station. So, our recommendation is that in these situations, it is really important to investigate expected traffic conditions before the decision is made. For scenarios with double-tracked line, the detailed investigation is not that needed on general basis. But also, for some situations, it might be important, especially in case of lines with heavy traffic. In such cases, it is a really good idea to use simulation approach. Thank you for your attention, and in case there are some questions, I'm ready to answer them. Thank you.
Thank you very much for this recorded presentation. Michael, if you are there, you can turn on your camera and your microphone, so we can start the Q&A session. If anyone in the audience has a question that would like to ask, please feel free to raise your virtual hand or just write a question in the chat. In the meantime, I've got a couple of things that I would like to ask. So first of all, you used this simulation software called OpenTrack, right?
Yeah, exactly.
Is it a commercial simulation software, or it's something developed by you, your group?
No, it's professional simulation tool for simulation of railway lines. It's developed in Switzerland. It's really famous, I would say, in the world of railway simulations, to be able to simulate traffic on the lines. And we have a commercial license.
Yeah.
And we have also academic licenses as well. So
okay. So it's really specific to rail, rail specific, let's say.
Yeah, exactly.
Okay.
Exactly. Yeah.
And so basically, you at the beginning mentioned that the platform, they restrict the capacity, if I'm right. But because I'm not in this field, how this happen? How platform restrict the capacity of the rail, like?
Yeah, because it's quite common to consider the situations when we move the platforms out of the station. That's the main idea that we've been focused in our paper. Is it's quite natural that it will somehow decrease the capacity, but it's not quite clear in which conditions it happens and how much it will decrease the capacity. So our investigation was focused on typical conditions in the Czech Republic when we have single line track between stations, how much it will decrease the capacity, and also quite common scenarios when we have double track lines between stations, and if we move the platforms out of the station, how much it will decrease the capacity. So that was quite interesting to see the results in, let's say, typical scenarios, and to get the results and to see if it's a single line track that it's a huge difference in the capacity. But if the line is double tracked, that it somehow decreases the capacity, but not that much.
Yeah, when you say, well, just to be clear, platform is basically where the passengers stand.
Yeah, it was in the first picture that quite common situation is to have the platforms right in the railway station. But if the railway station is quite far away from city center, it happens that the idea is, okay, let's build new platforms that will be out of the station and will be much closer to the city center.
Okay.
It was in the figure 1 that there are some options,
but then,
let's say, situations that we want to move it.
Yeah, but if you move only the platform away from the station, but in order to get to the platform, don't you need to access the station and get to the platform?
Yeah, of course, because the platforms are located closer to the city center, and the platforms, of course, will be accessible from the city center, and it's much more attractive for passengers to use trains if it's close to if it's closer to the city center. So that makes sense. And there were also let's say situations from the Czech Republic where when it happened in some stations, and it of course had some effect on the capacity. But there are, let's say, in our town, Pardubice, it is also under consideration whether it's a good idea to build a new, let's say, platforms near to city center or to keep it within the railway station. But it's quite far away from the city center right now.
Yeah, I see. And okay, thank you very much. Thank you very much. Interesting study, really. We have a question from one of the attendees, Mohayat. Please, you can turn on your microphone and camera and ask.
Thank you very much. Thank you, Michael Bažant, for the presentation. It's just a quick question about you said something about microscopic, macroscopic, and mesoscopic simulation in the railway simulations. I just would like to understand maybe better the differences between these three concepts. Could you elaborate, please?
Yeah, we are mainly focused on the microscopic simulations, because if we are focused on the small segment of line, not for the whole railway network, so it's quite important to put to the model all the details that are important. And if we do it, we call it microscopic level of simulation. I would call it like that. But in case we are focused on the whole railway network, for example, in the Czech Republic, there are so many lines and so many stations or some other switch areas and so on, then we are not able to do the model on such a detailed level. So in these cases, we talk about mesoscopic or microscopic level of simulation, because we are not able to put to the model everything on a detailed level. But in our research on the paper, we were just focused on the quite small segment of line. We talk about, let's say, 30 kilometers of line with 3 stations. So we were able to put everything, all the details that are necessary to the model. And in such a situation, we can talk about microscopic level of the simulation model. So for me, it was important to say it in the presentation that it's on microscopic level, to know that all the details that are necessary or important for the case study, they are there. Yeah.
Thank you very much. There was also a very interesting question. As a follow-up question, just one small. So what about the simulation software that you use and the computational time? Do you find, because you were like, okay, I cannot put a microscopic level to the whole rail of the Czech Republic because it's gonna be too much detail simulation, too big and too detailed. But does it also refer to the computational time, that maybe the simulation wouldn't be too slow?
Yeah, of course, both these nodes are relevant, but at first I would talk about whether it makes sense for for this type of study to make a model of the whole network. It doesn't make sense at all. For other purposes, it might be relevant, but not for the study that we did. But in case there are some problems that it would be needed to make model of the whole network, yeah, it is possible to do that in, let's say, OpenTrack or some other simulation software. But what's really time consuming is to enter all the data, let's say, on microscopic level to the simulation model. If you have, let's say, 2,000 railway stations and so many railway lines, it's really and of course you can then run simulation, and it will because we usually do 200 of applications to get really good statistical data. And in case you have the whole network with, let's say, hundreds of or thousands of trains inside the model, then it would really take quite long to compute it.
Yeah, I believe, yes. Yeah, thank you. I saw again Mohayat hands raised.
No, thank you. It was just a mistake. Thank you very much.
Okay. Thank you, Michael. Michael again. At the end of this session, we only missed one presentation, and indeed that's why we are ending a bit earlier. But it was a very interesting session. We had 4 different papers, some of them about rail transportation, some other it's more about air traffic, air transportation. And we had all the presentations were interesting and nice done, and we had nice discussion with the presenters. So I take the opportunity to thank all the presenters that contribute to this track. And also I wanted to thank all the attendees of this session. I hope you had enjoyed this session. And I want to remind you that we will have a break now, and then at 2 p.m. there will be other sessions. So please check the program and go attend the session you like the most. And then at 6 p.m. today we have the paper award ceremony. So please make sure you also participate there. And for the rest, I wish you a nice day and I wish you a nice conference. So have a good day. Thank you very much, all of you.
Thank you. Thank you very much.
Thank you.
Thank you.
Bye.